All right. If you're an engineering student, and especially if you're prepping for the GATE exam, you know that the memory hierarchy isn't just some random topic. It's absolutely fundamental. So today, we're going to break down exactly how it works and why it's such a clever, elegant piece of computer engineering.
So, it all starts with this fundamental dilemma in computer design. We all want memory that's blazingly fast, absolutely massive in size, and, practically free. But the laws of physics and economics have other plans. You're always forced to pick two. You just can't have it all, and that single challenge is the reason our computers are built the way they are.
Okay, let's really dive into this. Why can't we just invent one perfect type of memory, something that's super fast, has tons of space, and doesn't cost a fortune? What's stopping us?
Well, here's the deal. It really just boils down to physics and economics. The technology that makes memory super fast is also really complex and expensive to manufacture. So that speed, it costs you big time for every single bit. On the other hand, the tech that lets us cram tons of data into a small space for cheap is, just by its nature, slower to get information out of.
And that leads us to a really crucial point. A single memory solution is just completely impractical. I mean, if you built a computer using only the fastest stuff, it would cost as much as a sports car, and you'd be lucky to store a few documents on it. And if you used only the cheapest, biggest memory, it would be so agonizingly slow you wouldn't be able to do anything.
So, how do engineers solve this impossible puzzle? Well, the philosophy is kind of simple, right? If you can't have one perfect component, you build an intelligent system out of a bunch of imperfect ones. And the solution they came up with is a pyramid. So here it is, this beautiful hierarchy of memory types. At the very top, you've got CPU registers. We're talking the fastest memory possible, built right into the processor chip. Right below that, you have the cache. Then comes our main memory, what we all know as RAM. And way down at the bottom of the pyramid, that's where you find the massive but much slower storage, like your SSD or an old-school hard disk. Now, this is where the real elegance comes in. As you move down this pyramid, a few predictable things happen. The cost for each bit of storage plummets, the total size gets huge, but the time it takes to access data gets longer. But here's the kicker, the absolute key to the whole thing. The CPU actually spends most of its time accessing the fast, tiny, expensive layers at the top. It only goes down to the slow, cheap layers at the bottom every once in a while, and that is the secret.
And this brings up a super important distinction within the pyramid. The top layers, your registers, cache, and RAM, they're all volatile. What that means is they need constant power to remember anything. You turn the power off and poof, everything in them is gone. The bottom layer, your disk or SSD, is non-volatile. That's your permanent storage. It's where your operating system, your photos, your games, they all live there safely, even when the computer is completely off.
Okay, so how on earth does this pyramid, which is mostly made of slow storage, manage to feel so fast? It seems like it should be slow, right? Well, there's a secret sauce, a little bit of magic, that makes this whole elegant trick work.
I mean, this is really the million-dollar question. If the CPU needs data, and it's all the way down on the slow disk, why doesn't the entire system just grind to a halt? The answer, and this is so cool, isn't in the hardware itself. It's all about how software behaves.
And that magic has a name, the principle of locality. It's a fancy term for a really simple observation. It turns out programs don't just jump around randomly in memory, grabbing data from all over the place. Nope, they tend to work in small, concentrated areas for short periods of time. They're actually quite predictable.
This principle really breaks down into two super simple ideas. First, you've got temporal locality. That just means if you use a piece of data right now, you're probably going to need it again very soon. Like a counter in a for loop. Then there's spatial locality, which means if you access one location in memory, you're very likely to need the locations right next to it soon after. Think about processing an image or streaming a video, you're just going through data one piece after the other. And the entire memory hierarchy is built to take advantage of this predictable behavior.
All right, for all you GATE aspirants out there, listen up. This is where the rubber meets the road for your exam. We're going to shift from the why to the how you actually calculate the performance of a system like this.
Okay, so let's cook up a simple example. Imagine we just have a two-level system. We've got our fast level 1 cache, and let's say it takes 0.1 microseconds to get data from it. Then we have our slower level 2 main memory, our RAM, and it takes a full 1.0 microsecond. Yeah, a full 10 times slower.
So, the success of this whole setup boils down to one key metric, the hit ratio. Think of it like this. A hit is when the CPU asks for something, and boom, it's right there in the fast cache. A miss is when it's not there, and we have to make that long trip down to the slower RAM. So our goal is to get a really high hit ratio. For our example, let's say we have a hit ratio, which we call H, of 90%.
And this is the big formula you've got to know. This calculates the effective access time, which is just the system's average access time. Okay, so let's walk through this. That first chunk, H times T1, that's our best case scenario, a cache hit. It happens 90% of the time, and it costs us the very fast cache access time, T1. Now that second part, that's when we miss, which is the other 10% of the time. And notice the cost here. You see that T1 plus T2? That's the penalty. You waste time looking in the cache first, which costs T1. Then you have to go all the way to the slow RAM, which costs T2. You pay both prices.
So, what's the big picture here? Because of that principle of locality we talked about, we can usually get a really high hit ratio. And when that happens, the average access time for the whole system gets incredibly close to the speed of just the fast cache. It's like we've pulled off this amazing magic trick on the CPU, making it think it has this gigantic, super fast memory to play with, hiding the slowness of everything else.
All right, let's bring it all home. Let's pull all these threads together and do a quick summary of what this is all about.
So, to wrap it all up, the memory hierarchy is, at its heart, a clever engineering solution to an economic problem. The whole goal: get the speed of the crazy expensive stuff with the size and cost of the cheap stuff. And how does it work? It all hinges on exploiting that one simple, predictable behavior of software, the principle of locality. And that's why the system is organized so that the CPU rarely has to talk to those slow, lower levels.
And that leaves us with one last, kind of cool, forward-looking question. You know, for decades, this pyramid structure has been the bedrock of computer design. But new tech is coming. Things like persistent memory that's fast like RAM, but also remembers things when the power's off, like an SSD. This new technology is starting to blur the lines between the layers of this pyramid. So the real question is, what will this memory hierarchy even look like 10 years from now?